From the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, welcome to the NASA New Horizons mission Countdown to Pluto. I'm Mike Buckley from APL Communications and Public Affairs, coming to you from Pluto's doorstep as we count down to New Horizons' historic flight through the Pluto system on July 14th. We're 4 weeks from the Pluto flyby, just under a month. New Horizons itself is now just about 20 million miles from Pluto, closer than Earth and Venus at their closest point. And after 9 years and 3 billion miles, it really feels like 2015 is the year of Pluto.
There's a mysterious zone far out in our solar system. It's a region of ice worlds, some solitary, some with moons. Their names may be unfamiliar. Eris, Makemake, Haumea, but they hold clues to all our origins. And the first of these worlds, and the one we'll reach in 2015, is the king of the Kuiper Belt, Pluto. The long journey of NASA's New Horizons mission began in 2006 aboard America's biggest, baddest rocket, tricked out with every conceivable booster.
We built a very light spacecraft and bought a very large launch vehicle, and the combination is ferocious.
But in some sense, it all began in 1930 with Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, but willing to spend long hours scanning star fields to find a moving point of light. Humanity's first glimpse of Pluto. The dream of actually getting to Pluto began with a 6-year-old boy in love with science, who grew up to lead a team of brilliant researchers and engineers with dogged persistence through decades of planning and building and testing. A race against time just to get to the launch pad.
Exploring the outer solar system, because it's so far, takes a lot of time. It requires a lot of patience, a lot of dedication, a lot of perseverance, but it's the frontier.
Assuming all goes well at Pluto, NASA may choose to extend the adventure further out into the Kuiper Belt, the solar system's mysterious third zone.
This is maybe the one chance in my lifetime that we're going to get a spacecraft out there and look up close at one of these Kuiper Belt objects.
December 6, 2014.
We have long to wake up with the New Horizons spacecraft.
New Horizons wakes up for the last time from hibernation.
New Horizons is speeding towards Pluto at a phenomenal rate, and we can't wait for it to get there.
January 27, 2015, 6 months of approach science begins. July 14, 2015, New Horizons' long journey, 3 billion miles, 9 years in flight, and 85 years of speculation about Pluto, climaxes in 1 day of close approach and flyby.
You know, we're rounding third base and we're headed home.
The dream, the adventure, the promise of discovery. That's what makes 2015 the year of Pluto.
That was a look at the year of Pluto, the story of New Horizons, now running on the mission website and NASA TV. And now let's get an operations update. Now, the year of Pluto covers the New Horizons team as it prepares for this summer's flyby. And a familiar name in that video is Mission Operations Manager Alice Bowman. Alice, thanks for joining us.
Hi, Mike.
Let's just start first by telling people, this is a big team. What does a Mission Operations Manager do?
Well, the Mission Operations Manager manages the Mission Operations team. We have about 20 people on the Mission Ops team, and they're composed of planners, and they're the people that are responsible for building the command sets, testing, verifying them before they go to the spacecraft, and also ensuring that those commands do what the scientists want the instruments to do and what the subsystem engineers need to have their subsystems be doing to support this incredible encounter. We also have flight controllers. They're the people that sit what we call in the command pit, and they watch the data come in from the spacecraft, monitoring for any kind of off-nominal or abnormal conditions. They're also responsible for sending commands to the spacecraft.
Those are the commands that tell the spacecraft what to do. That's
yes.
What happens. Okay, so you're doing a lot of communications with New Horizons, but for something that's 3 billion miles away, that has to present some special challenges of its own.
Yes, it certainly does. It's much different than communicating with a spacecraft that's in orbit around Earth. For one thing, we have to account for the amount of time it takes for the data coming from the spacecraft to reach Earth. So we have to send that data from the spacecraft a little less than 4.5 hours before we're ready to receive it on the ground with the deep space antenna. Likewise, when we want to send information or commands to the spacecraft, we have to send them to the point in space where that spacecraft will be a little less than 4.5 hours later. So the spacecraft may be here when we start to send those commands, but we're actually sending those commands to this point. And as those commands travel through space, that spacecraft will come down and will intersect and it'll receive the commands from Earth.
So this is like a deep space forward pass. I mean, you really have to make sure the receiver is in the right spot. You've got to get it there to get those commands too. There, it's also something interesting too about this is that the team seems, with that communication, you kind of have to pick your spots in a way too, because understand the spacecraft can't communicate, it can't send data back or receive it when it's collecting data, say if it's focused on the Pluto system. So how does the team work that out?
Yes, that's very true. One of the things that we did to ensure that the spacecraft gets to the Pluto system healthy was to minimize moving parts. And so we have this gigantic antenna on the spacecraft, but it's fixed. So and those instruments on board the spacecraft are co-aligned with that antenna. So in order to take data of the Pluto system, you have to point that spacecraft to those objects that you're taking images of or collecting data on. And when you want to communicate with Earth, you have to turn those instruments away from their data taking and point to Earth. So what we do is because the science team wants to maximize observations of Pluto, they have specific times where they're observing, and all those other times we will point that spacecraft to Earth and send data. Likewise, we'll be able to send commands when the antenna is pointed to Earth.
Right, take your chances when you get them. Your opportunities to get that when it happens. That's a busy spacecraft and a lot of activity. So I'm thinking as we're getting close to flyby, your team has to be pretty busy too. Tell us a little bit what's been going on the last week or so with the operations team.
Sure. We have a lot of things going on in mission operations. We have 4 different command sequences in development, spanning from about 2 weeks in the future through 6 days after closest approach. So we're testing, verifying, building all those command sets, getting them ready for uplink to the spacecraft. We're having critical design reviews, etc. We're also watching all the activities that happen on board the spacecraft that we planned about 6 weeks ago. And these things include monitoring to make sure that everything's going like we expect it to go. We're bringing back down a lot of data, light curve data, air glow data, plasma data. We're also bringing down optical navigation data, and this is data that the navigation and mission design teams are going to use to determine whether or not or when we need to do trajectory correction maneuvers.
All right, that's just to make sure too that the spacecraft is on course, right? That it's going to get to its aim point at the right time near Pluto to see if you have to change or make those moves.
Definitely.
So how are things on board? Spacecraft is healthy, things are looking good?
The spacecraft is great and the team is ready.
All right, thanks, Alice. Sure. And now for a science update. To talk science is Kathy Olkin, a deputy project scientist for New Horizons. Kathy, thanks for joining us.
Thanks for having me.
Let's just start first. Explain a little bit about the role of a deputy project scientist on New Horizons.
I have a number of different responsibilities on the New Horizons mission. I help with the Pluto encounter planning. I also review the sequences for the Ralph instrument to make sure that everything we're going to send up to the spacecraft executes as we expect it so that we can get the best science return.
What kind of science data has New Horizons taking now? I mean, we're kind of on approach, we're looking in. What kind of data is it gathering on the system, even from far enough away?
So we're getting lots of interesting data right now. We're getting data with the LORRI instrument. We're getting interesting maps of the surface. We're getting hazard data. We're getting color images with the Ralph instrument and plasma information from the Plasma Suite, SWAP, and Pepsi.
You mentioned LORRI too, and we have some new images that just came out from LORRI too. Let's take us through some of those. What are we seeing in those pictures?
Yeah, this is getting really exciting. Here you can see 4 different faces of Pluto. We have 4 different images taken with the LORRI camera, and you can see down at the bottom here this dark region of Pluto. So this is really interesting. We've always known that Pluto has dark and bright regions, but now we're starting to see how large they are, where they're exactly located, what shape they take. And it's very fascinating to see this level of detail.
So I mean, we're getting closer and closer. It's getting harder and harder for Pluto to hold on to its secrets.
Most definitely. It really is.
So what observations are planned over the next week or so?
We have a lot of exciting things coming up this week. We have the first observations in the infrared with Pluto and Charon from New Horizons. So I'm really looking forward to that. We also have a series of daily MVIC color images that we'll be taking of Pluto and Charon to cover a whole rotational phase of Pluto. And we have LORRI images continuing. So.
Okay, well, thanks, Kathy.
Thank you.
Of course, all of this leads up to the flyby on July 14th, when New Horizons makes observations of Pluto and its moons as it zips through the system at more than 30,000 miles an hour. Now let's take a look at what New Horizons will be doing as it passes Pluto, besides making history.
So July 14th is going to be really exciting. We have observations planned with our whole suite of instruments.
Things really begin to heat up at about 3 hours before closest approach.
As we're flying by, if my hand is Pluto, the spacecraft will fly by and it'll scan the LISA instrument across the surface of Pluto to build up a spectral image of what the surface looks like.
Then as we get around toward Pluto's terminator, we take our very long, high-resolution scans in black and white, which means that we can use the very wide field MVIC and at the same time use the narrow field LORRI. So we get 5,000 pixels across Pluto, about half a kilometer resolution at closest approach. At the same time, we have this very skinny inset of the LORRI field of view at only about 100 meters per pixel. So we take our LORRI images one after the other, these overlapping images. So what it looks like is this big plate of Pluto and this skinny little noodle of LORRI running across the middle. At this point, we are, for the first time in humanity's history, behind Pluto, taking pictures back on the far side.
The ALICE instrument will be doing a solar occultation, which is watching the sun set behind Pluto. The Deep Space Network will be transmitting a signal, and that signal will be picked up by the antenna, and it'll be changed by the atmosphere of Pluto that it has to go through. And that's how we probe Pluto's atmosphere, the pressure and temperature right near the surface. July 14th is the apex of what we've been working for. We launched more than 9 years ago, and ever since then we've been trying to shepherd the spacecraft safely across the solar system.
As spacecraft goes, New Horizons is a very small team, but still we've been working on this for over a decade, and you add it all up, and it's about 2.5 million work hours to get ourselves to Pluto.
We can't wait to get to Pluto and to July 14th and see what the surface looks like. We're ready to go, and it's showtime.
Now, of course, to get great data, you need a great spacecraft. And New Horizons carries a range of tools and capabilities for its mission to Pluto. Now, joining me for a look at the spacecraft is Mission Systems Engineer Chris Hersman from the Applied Physics Laboratory, where New Horizons was designed and built. So Chris, thanks for joining us.
Well, thanks, Mike, for inviting me. It's a pleasure to be here.
It obviously takes a team to build something like New Horizons, so maybe tell us a bit about the Mission Systems Engineer's role on the spacecraft team.
Oh, thanks. So the Mission System Engineer is the lead technical person on the project, but he can't do his job without his team of experts in the fields. I was the spacecraft system engineer during the development, and I had about 10 leads, one for each of the subsystems on the spacecraft. I had the power system lead, the propulsion system lead, the thermal system lead, communications, command and data handling, all of those people together. And if I've left out any, I'm sorry. But all of those subsystems together, they really they're the experts, and they're the ones who actually make it happen. And I was responsible for the interfaces between the subsystems and between the systems and the instruments. And then now that I've taken over the role as mission system engineer, I'm also responsible for the ground system, the instruments, and that as well. But again, it's the technical experts and the leads that really make it happen and pull it all together.
And it's been working, over 9.5 years in space, over 3 billion miles to get there. So I guess, how do you design something, okay, not just to go so far, but really to go where no other spacecraft has really gone before?
Mm-hmm. Yeah, we started with the power source because we really had to use the radioisotope thermoelectric generator because there's not enough sunlight to really power anything out at Pluto. So given that, it only has about 200 watts of power when we get to Pluto. So we had to design into every subsystem ways to cut power and to shave a few watts here and there to get under that 200 watt limit. And we managed to do it with developments like the digital receiver, which we built here at APL. That was an enabling technology. We also had sophisticated thermal control that would allow us to operate at Pluto without any electric heaters. We actually reuse some of the waste heat on the power source. We also have a software-controlled algorithm that keeps the level of power inside the spacecraft to maintain the constant temperature. And right now, the spacecraft is approximately room temperature on the inside. When outside, it's almost a couple hundred degrees below 0 Celsius.
I mean, so the idea that just by operating, it keeps itself warm. The electronics and the boxes, everything, as they're moving, that keeps the spacecraft warm.
That's right. Just like the way your laptop gets warm, all the boxes inside, they get warm, and then they keep a tight thermos bottle design on the spacecraft to keep that heat inside. And there are also some components that actually want to be cold, and they are actually put outside of that thermos bottle. And then they actually try to minimize the exchange of heat between the various isolated components from the ones that are inside that need to stay at room temperature.
Okay. All right, so Chris, why don't you take us for a tour around the New Horizons spacecraft?
Oh, I'd love to. Here is the New Horizons spacecraft, which shows a triangular shape which is used to balance the spacecraft. The size of this is about the size of a grand piano. And what we did is we positioned all the instruments in the view that you see here, pointing in the direction opposite of the power source, which is this black curling iron type object over to the right. So we put that actually out further because it generates heat and it also generates radiation that could affect the electronics. So in general, we put all the sensitive electronics on this side of the spacecraft, the left side, and put the power source on the right side. And that provides two things. It provides distance between the two. It also provides balance for the spinning mode of the spacecraft. And we have a spinning mode. That's one of the things that helps us get through this long duration mission, because when we spin the spacecraft, it doesn't take any fuel to maintain the pointing. And then we can put it into a hibernation mode where we turn most of the electronics off, which lets those electronics last longer. And it's just, it all ties together into the operational mode that we use for the spacecraft. So if we move down to the first instrument that I'd like to show you, it's the ultraviolet instrument. It's called ALICE. So the ALICE instrument shown here is the ultraviolet instrument, and it will measure air glow in the atmosphere as well as taking occultation measurements as the spacecraft traverses into the shadow of Pluto. And simultaneous with that ultraviolet measurement, they'll also make a radio science measurement from signals that are transmitted from the Earth at the same time as it's traversing into the shadow of Pluto. And then the next instrument I'd like to talk about is the RALPH instrument. This has the ultraviolet and visible imaging that's used at the closest distances to get the full view and the composition mapping. They use the infrared part of the instrument to determine the surface composition. And like I said, the ALICE instrument was measuring the atmospheric composition. So if we move on to the other side of the spacecraft, you'll see the radioisotope thermoelectric generator. And this is connected to the spacecraft through a pyramid shape, and that pyramid was actually altered during the design to minimize the amount of additional weight that you would have to put on the spacecraft to balance it. So we could adjust the design of that pyramid in a shape so that it could move it further away or closer or up or down. And then we set that, once we built that pyramid shape, and then installed that right on the launch pad. You'll also notice the heat shield, which is the gold octagon-shaped object between the power source and the spacecraft. And that's designed to minimize the amount of heat that would be coupled to the instruments to adjust to cause noise in the instruments. But there is actually a tailored opening inside of the spacecraft that allows some heat to come through and keep the inside of the spacecraft warm. So now moving up to the high gain antenna, you can see here there's actually an assembly of multiple antennas. At the very end is a low gain antenna, and that was used at launch, and it can see half of the sphere from the spacecraft, and there's another one on the other side to give full coverage from all angles of the spacecraft. That allowed us from the ground to talk to the spacecraft no matter which direction it was pointing. Then in the middle there is a smaller dish. That's our medium gain antenna, and we use that for beacon modes and also for emergency modes to have a wider beam width than the high gain antenna, and that's very important for communicating during the hibernation period. Then the high gain antenna, that's the one we use for the radio science and the high data downlink of the science data after Pluto. So moving over to the particles and plasma instrument, you see here the solar wind at Pluto instrument. The SWAP instrument can make measurements on the atmosphere even when the optical instruments are taking images of Pluto. And we keep those instruments on throughout the encounter so that they can measure, and there's actually an interaction between the solar wind and Pluto's atmosphere that creates a bow shock, and that's one of the critical measurements that this instrument will make. There's also an energetic particles instrument, which is shown here. It also has a fan-shaped aperture, and it measures the energetic particles, but it doesn't actually want to see the sun. It wants to see the ions that may be coming off at high velocity, and it measures the mass and the time of flight of those particles, and by there it can determine the elemental composition. And then if we move around to the backside of the spacecraft here, you can see the long-range imager, and this is about 1/3 of a meter in the aperture, and it takes the images for optical navigation, and also it'll take small high-resolution images while the other Ralph instrument is taking larger maps of the surface. And we also have underneath the spacecraft a student dust measurement counter that will count the impacts of dust particles from the region around Pluto. And then moving over to some of these other cameras, this is the STAR camera, and it's an interesting set of cameras. There's actually two. We only do one, but we have two for redundancy. And the STAR camera has 2 modes of operation. It'll operate in a spinning mode or a 3-axis mode. And that was very important for our hibernation period as well, to have some attitude knowledge while we're traversing in a spinning mode.
Now, when you say 3-axis too, I mean, that's when the spacecraft is actually configured almost still to move around to take data.
That's correct. When we take images, we're in a 3-axis mode, and that's important, otherwise all the images would be blurred. When we're in a spinning mode, we don't take image data, but we can still take the particles and plasma data. We can also take the student dust counter measurements. So moving on over here to the sun sensor, just in case the star tracker has a problem and it can't get a lock on the stars, and we need to go to a safe mode, we keep on board a sun sensor so that we can point to the sun. Even if we don't know what day it is, if we don't know anything else, we can always point to the sun, and we know that we'll be able to get commands in through the medium gain antenna.
Because you know that far out too. I mean, if you're just pointing at the sun, Earth is nearby.
That's correct. It's very close in the region of the sky, and that was why we designed this. We didn't need it for power, but we do want it for the ability to communicate. So if we lose the time on board, we can always point to the sun. So we defined that as the lowest level of safe mode for the spacecraft in case it loses track of time or doesn't know where the Earth is. It can't find the Earth. So that's the tour of the New Horizons spacecraft.
I mean, it sounds like the design has proved itself out so far. Right? I mean, 9 years in space, 3 billion miles, and it's still working and working well. It has a job to do at Pluto, right? And it may have a job to do deeper in the Kuiper Belt with NASA's okay. Just how long could the spacecraft go? How long could it last?
So the thing, if everything all goes well, we've done some estimates on the amount of power that we can have at the Kuiper Belt, and our Kuiper Belt looks like we'll have about 12 watts less. So we actually have to budget. What can't we save in power? And we've already come up with strategies for that. And then we said, how far do you think we can go? How low can we go in power and still keep operating? And we've made a conservative estimate on what we could do for a mission beyond the Kuiper Belt. And there are a lot of interesting interactions between the heliosphere and what's beyond that. And so we'd like to get there. And it looks like we can make it until the mid-2030s at least, assuming nothing goes wrong, and we're all superstitious, knock on wood. But yeah, it looks like 2030 is, mid-2030s is where we're predicting we could at least, conservatively get to with the power that we have on board.
Well, this has always been a mission of patience to begin with, right? So there's a few more years after this. So, all right, well, thanks, Chris.
Thank you, Michael.
Out on the fringes of the solar system, where New Horizons will encounter Pluto, sunlight is much weaker than it is here on Earth. But it isn't completely dark. In fact, it's a bit brighter than you might expect. For just a moment near dawn and dusk each day, the illumination on Earth matches that of noon on Pluto. And we call this Pluto time. And NASA recently introduced a web program that allows you to find Pluto time in your area. You start by plugging your coordinates into the map, and then find out when it's Pluto time in your area. Take a picture during your local Pluto time, and share it to social media with the hashtag #PlutoTime. NASA will highlight some of the most interesting shots from around the world. Next month, after New Horizons makes its historic flight past Pluto on July 14th, we'll combine as many submitted images as we can into a mosaic image of Pluto and its moons. That's pretty cool. So that's the latest from NASA's New Horizons mission on Pluto's doorstep. 28 days and 20 million miles to go until the flyby. The countdown to Pluto continues. I'm Mike Buckley from the Johns Hopkins Applied Physics Laboratory, and we'll see you next week.